instance, right? So you have two different proportions, 10 out of 30, and the second one is 15 out of 40, right? I'm just making up random values, right? Now, when we do our typical standard error, which really is the go-to standard error, that's what virtually every real standard error should be like. You treat each of these separately, and you know you're going to get the P1, whoops, Q1 over N1, P hat 2, Q hat 2 over N2, right? You're going to get that. When you pull it, you have a new guy called P hat, and basically you add the number of successes and you add the total number, and that's the new guy. And when you do a P1, P2 hat standard error, but you use pooled, the formula for the standard error becomes big P hat, big Q hat over N, and N now happens to be the combined total of 70. Do you see that these are not the same number? Can you imagine that if you use the individual values, this might be 0.2 and this could be 0.27. And that is the most likely reason that you might be getting different values, significantly different values. Now, unless I very specifically say this data is going to be pulled, we are working on the assumption that the data is independent, which really is a better assumption, because if you're pulling the data, what you're saying is that the two groups, although they may have different values, behave the same way. In other words, the variation is roughly the same. That is a very big assumption that you really shouldn't make unless you've got really good reasons to do it, which is why I avoid that assumption, because I don't think it's a good assumption to make. It's much safer to make the assumption that they're independent, and that's much more realistic. And even if they weren't independent, it's still safer to assume that they are, right? So if they two they behaved in similar ways and their distribution would be the same. Now, there's another formula when you do pooled data and it's means, right? And I haven't even touched on that formula, so if you want to look it up, you can. It's in the textbook, and that is the same kind of reasoning here. You have two different samples, and you're assuming that they behave in the same way, and therefore you can pull the data. I hope there aren't any questions like that. I filtered them as best I could, so I made sure that they didn't ask that. But there is a chance that one of them might have sneaked through. Do you want us to look at one just to check it out, or is that enough right now? And maybe you can go back and check some and say, yeah, that's kind of what happened. They were using pooled when they shouldn't. Well, I can't say when they shouldn't, but they were using pooled but didn't tell me.
I guess I'm not so concerned about, I mean, like for your test, I feel fine. It's just, I'm missing points on my homework, and I don't really want.
No, I don't think you should lose the point. So you just give me a list of the ones that did that. I'll double check that that's the real reason things didn't work, and I just give you the points back. It's easy fix. Now, I mean, in the real world, when you go out and you do this, you may well decide from time to time to use the pooled data. If you do, you really should justify it. I find it hard. I know it can be done, but I find it hard to justify it. So that's why I'm not focusing on this one. Any pooled data, I think. And I can see a situation. Can you imagine it was men 10 years ago and men right now? You could say, well, they're probably the same kind of distributions, right? They're probably going to vary the same way. You could probably pull the data then, right? I could imagine that would be a situation where I think I'd be comfortable with pulling it. But if you said males and females, I don't think I can really feel comfortable that they are actually going to be the same kind of distributions, right? There might be, differences in there because of that. Okay, that was a good question. Has anybody got a specific topic, or do you want me to just start at the beginning and just, go through it and pick topics as I see them. Okay, so, here's a big list of them. I think I got them all. Data collection, summaries and graphs. That was obviously in our first week or two. What we're doing here, well, we're looking at all the kinds of things that you do when you start off statistics. One of the things we can look at, for instance, is bias data. Or what we really want is unbiased data. A lot of these questions can be multiple choice because they tend to be stories followed by why is this a bad idea? Or can you think of reasons why this might not be good? Off the top of my head, I collect 200 random people and I asked them, are you in favor of higher taxes? And I get an answer. And then I grab another couple of hundred people and ask them a question, are you in favor of higher taxes to pay for child welfare? Now, the fact I added on the second question for child welfare, do you think I'm going to get the same kind of results when I just said, are you in favor of higher taxes? I would suspect that more people are going to say, yeah, I'll pay more taxes. You know, I want children to be looked after, right? Child welfare seems like a good deal. I would do it. And that's an example of introducing bias in the way you ask the question, right? Which is very common. You can ask, can't you get bias in all sorts of ways? We've gone over most of them. If you ask people how often they have stolen things in the last year, you tend to get bias, response bias, right? People tend to tell lies if the question is personal. Can't you get bias by who you ask? I was interested in, are you in favor of higher taxes? So I went to high-end golf resorts and only asked the members. Can you imagine that might not be a good sample if I wanted unbiased data, right? So can't you get biased by the people you ask if you're not being random enough? Anybody think of any other ways in which you can bias data? Nothing?
Maybe if it's something on, you're the person that's asking and it's about you. Like if I
Oh,
were
yeah.
to say, do you support mothers in the workplace and I have my child next to me or something?
That is a good one. Yes. Yes. It's a good one, right? Yeah. Yeah, I've never thought of that, but that's true. I mean, if the person who's asking the question is somehow connected to the question that's being asked, couldn't that elicit a change in response? So if an old guy was asking a question like, should they reduce taxes on people who are over 70? And it's an old guy who's asking you that question. I could imagine that you might change your answer because of the person who's asking and it's connected to them. I've never thought of that one. It could happen. Yeah, I could see that happening. Right, so you've got your good data. We have lots of summaries, don't we? We have means, we have mode, we have median. Do a question like this then. Suppose I had data that was skewed to the right. Forget about the mode. The mean and the median. Which one of these two would be the bigger if the data was skewed to the right? Would the mean be a bigger number or would it be the median? Actually, the median would be more over here, probably. And the answer is the mean will be bigger. Why will the mean be bigger than median if your data is skewed to the right then? You think about calculating the data. When you calculate the mean, isn't the value of every number counted? So if your data is skewed to the right, won't that be, there'll be a few, if not quite a lot, of quite large numbers. And what do large numbers tend to do? They tend to make the mean bigger, don't they? But when you do the median, you don't care if the numbers are big or small. Doesn't each number just count as one position? And so you tend to get the median further to the left. How about this question? If you have an outlier, right, an exceptionally big number, exceptionally small number, will the mean be affected badly with an outlier? Will a median be affected badly with an outlier? No. So means get affected by outliers, medians don't. So if you imagine I could have a story, this would be a multiple choice. Most of these questions I'm talking about right now are multiple choice. Couldn't I have a story about you collected data on 100 people and Bill Gates was one of them, right? And you asked them how much money they had in the bank. Wouldn't the mean number be extortionately big because of Bill Gates? But wouldn't the median of the class be bang in the middle, you know, $200, you know, something like that? That would be the effect, that, you know, the outlier effect. You can also have in this group of questions things to do with Z-scores. Z-scores allow us to compare fairly, for want of a better word, two distinct situations. And the ones that I've used before are things like John got something in a test and Mary got something in another test. But let's change the story now. Let's suppose we looked at, think of something else. Yeah, I started thinking something at the top of my head. Okay. Let's suppose that you looked at two different countries. We'll call them country A and country B. And in country A, the average child family size is two children in the family. And the standard deviation was 0.5. And in country B, the average was 4 children in the family. And the standard deviation was, say, 1. And you had somebody in country A and somebody in country B. And in country A, this family had 5 children. And in country B, this family had 6 children. And the question is, which of those two situations is more extreme, right? More unlikely, all right? Is it harder to have 5 children in country A? Is that more unusual than it is to have 6 children in country B? Well, superficially, isn't 6 children more than 5? So you might think this one is the most unusual. But when you take into account the mean and the standard deviation, it's not necessarily the case. And the way that we compare two things then is we calculate their Z-score. And isn't bigger Z-score more unusual, harder to get? So if I did this one, the Z-score would be 5 take away 2 divided by 0.5, which is a Z-score is 6. And if I did this Z-score, it would be 6 take away 4 divided by 1, which is 2. So having 5 children in country A is much rarer event than having 6 children in country B. But what we've now been able to do is do a fairer comparison, right? Now, since I've got these numbers, isn't country A not just a rarer occurrence in country B? Isn't country A even a rare occurrence within country A? Isn't a Z-score of 6 like way out there? You know, aren't Z-scores meant to typically be between -3 and 3? So somebody with a Z-score of 6 would be like a 1 in 1,000, a 1 in 10,000 more likely situation, right? So we can use Z-scores. We can also do one of these things. Oops, wrong notation. A population has a mean of 30 and a population standard deviation of 15. That's by choice, 10. You can do one of these fellas. Right in the middle goes 30. Can you remember the 1, 2, 3 standard deviation, normal distribution thing? In this case, 40, 50, 60, 20, 10, 0. This will test your memory. Within 1 standard deviation of the mean, within 2 standard deviations of the mean, and then within 3 standard deviations of the mean. And it's called, I believe, in this textbook, at least, it's called the empirical rule. Okay, what percentage of all the people would be within 1 standard deviation? Can you remember the magic number?
68.
That's the one. 68% of data tends to be within 1 standard deviation of the mean. A little bit harder number. Can you remember what 2 was? Oh, we can. Anybody?
95.7?
You combine 2 different answers. I know where you're coming from. It's 95, but not the 0.7. And then 0.7 that you wanted to use. You remember them now, the 68, 95, 99.7 rule? Vaguely. So with that kind of information, you can actually make predictions on how unusual something is. Can you see why somebody whose Z-score is 6, which really just means there's 6 standard deviations away from the mean, why that is such an exceptionally unusual number? Side issue. This is true information. The gist of it is true. We have good data on deaths caused when accidents happen at certain speeds. I'm just going to fill in the numbers because I'd have a horrible memory, but the gist of what I'm saying is true. If you were traveling at 90 miles an hour and you have a crash, right? You know, hit something that's not moving, pretty serious, you might have a 60% death rate. In other words, 60% of the people who smash into a brick wall at 90 miles an hour die, right? And the others are probably very seriously injured. if you hit a brick wall at 60 miles an hour, that death rate, 40% of you say die. If you hit a brick wall at 30 miles an hour, let's say 20% of you die. There is a definite pattern here, isn't there? And you can see that common sense tells you that the smaller your speed limit, right, the smaller the speed you hit a brick wall at, right, the more chance you have of surviving, right? Now, if you are using this data, there is always going to be a situation where you have to do the following. You have to do risk, benefit. It's a too strange thing. You have to do a risk benefit analysis on any decision that you make. Argument one might be done by a politician like this. We lose 50,000 people a year due to car accidents. One of the biggest causes of death is the speed at which the accident happens. Therefore, we will reduce the speed limits onto all the roads, depending on what kind of roads, different speed limits. And that will reduce the number of deaths. And that would be true. It would reduce the number of deaths. So there is a definite benefit to that, isn't there? Right? You reduce the risk, the benefit improves, right? But unfortunately, you can take that argument too far. If you use that argument, shouldn't all motorways have a 30 mile per hour speed limit? Wouldn't that save lives? Of course it would. Right? Well, assume people, those who speed are going to get, different issue, right? But let's assume most people are honest and, if the speed limit's 30, they'll do about 30. That'll save lives. So why can that go crazy? Well, do you think we should have a 30 mile an hour speed limit on motorways? I mean, what's the opposite effect? Well, people's lives get saved. That's always good. So what's the negative? What's the risk?
It'll take forever to get anywhere.
It will. It'll take you forever. Now, let's just suppose, and God, we have some dumb politicians, somebody, brings on a poor little child and says, this is, her mother was killed on a motorway accident. And if she'd been traveling at 30 mile an hour, she'd be alive today. And this poor little kid wouldn't be an orphan, right? Those kind of things that they love to do, politicians. Bring on kids, makes you feel bad. Whatever it is, you'll say, okay, let's do it. If you made it 30, then why don't we make it 15 miles per hour? Because won't that save even more people's lives? Okay, then, I'm going to hit a number where everybody here is going to say, oh, come on. Shouldn't we make it 5 miles an hour? Won't that save even more people's lives? Don't you have to do a balance somewhere? Don't you have to say, this is the speed limit? And yeah, people are going to die when they crash at this speed limit. But we can't make everybody go 5 mile an hour so nobody dies, because nothing. Do you want to live in a world where you do that? So risk benefit is something we got to do. Let's be silly. People die falling down stairs, don't they? Should we make it a rule now that all houses don't have stairs? Won't that save lives? Because you won't fall downstairs, there aren't any. Can you see where I'm going with this? You can take something that says quite sensible, you will save someone's life, but if you take it to a certain extreme, the risks aren't, the benefits don't help the risks. We have to live in a country where people take risks. Otherwise, life is really boring. Me personally, I don't smoke. But I'm not going to ban other people from smoking. As long as they understand that there's a very strong risk you'll get cancer and it's certainly bad for you, it's not my job. Me personally, I don't have problems most of the time with people taking drugs. I think you're stupid to do it. I think you're daft to do it. I think it's one of the worst personal decisions in your life. But it ain't my job to tell you to do things. Nor should it be the government's.
What's your thoughts though on the stress or what smoking does? It's not just that a smoker smokes and they might get cancer. That smoker then racks up hospital bills and
Well, that's true.
healthcare workers, and
Yeah.
it's no longer just them.
So what you should do then is just say, if you're going to smoke, have insurance. Right. You might ride a bike, David. You could fall off that bike and break some very important parts of your body. That's going to rack up insurance, medical bills, and hospital time. Should we ban people using bikes? Anything that involves, you go hiking, skiing, should we ban those because people get hurt?
I think what you're saying is, where does it stop? So if smoking is an issue, obesity is a huge issue.
Yeah.
Should we stop selling potato chips and sodas and whatever force people to work out an hour a day? So there's always a step up. There's never an end.
The life is full of decisions, and I can understand that society decides certain things need laws. I think you need speed limits. I'm not saying don't have them, right? I think it'd be carnage to just say to Americans, travel any speed you like on any road you like. Would you get out and be a dumb rule, right? All I'm just trying to say is that you have to figure out where that magic balance number is, don't you? You can't do it at 5 and you can't do it at 150, but you have to balance it. But I'm not right. That's just an opinion, right? I'm not right. But neither are most politicians. I always figure out if a politician wants something, I'm against it. Because 9 times out of 10, I'm probably going to be right. But that's me. Okay, let's move on to chapter 3, regression lines. They are cool things. Star plot. So you have along here, you have, I don't know, age. You have up here height, measuring children. You get a nice straight line. Remember regressions? Good stuff, isn't it? It's a way of comparing two variables and generating a linear formula, typically. Let's add some multiple choices. It seems to me what I'm doing today. Is this data positive or negative association?
Positive.
Yeah, great. We then get into that grey area. Is it moderate? Is it weak? Or is it strong? Right? We there's a little bit of grayness here, but it's definitely not weak. I think it's probably moderate or strong. You get an equation for this. Let's suppose that your predicted height of this creature, let's say it's some animal, is 10 plus 3 times its age. So we've collected data on baby mongooses, whatever they are, right? And it takes 3 years to become an adult. And so this is the ages of various mongoose babies, and we've measured their height, and we got this formula here. And this is a regression equation, right? And you can use it just the way you normally do an equation. If you wanted to know what the typical 2-year-old mongoose is, it's 16 whatever inches. Say the units are inches. Good formula, right? You can use it. There's some numbers that we attach to that. there's a guy called the correlation coefficient. Let's suppose in this story it's 0.7. Could be. There's another guy called R squared, which we typically convert into a percentage. What does the 49% tell us? If this was a 49%, sometimes called the coefficient of determination, if it was 49%, wouldn't that basically be saying like there's a 49% fit? The fancy sentence is that 49% of the variation is accounted for by the model, right? But that's not a very good fit. Would you agree that half the time you're probably going to be miles away and half the time you're probably going to be pretty close? So that, if that was the correct number, that would probably be more like the moderate or weak to moderate, now that I've given it a number. Suppose we had this formula for baby mongooses. And I did this. I used it to predict the age of a 10-year-old mongoose. And the answer I got was 40. That answer is silly. It doesn't make sense. And the reason it doesn't make sense is that I'm using it to predict the age of a mongoose, but my data was based on baby mongooses up to adulthood of 3 years. Would you agree that most creatures, once they reach adulthood, that's as big as they get tall-wise, right? And so using this number, which is beyond the range of the data, is very dangerous. And they have a word for this. It's called extrapolation.
I think there is a way of writing it that displays that. I don't remember how though.
Well, the extrapolation?
No, it's like next to it, like in parentheses, it shows like where it starts and where it ends. That's if you have
could,
graphs
yes.
with a lot of different types of sections for the same thing.
Right. You could have a little limit like that that basically says only use this model in the range 0 to 3. Now, I can use this model to predict, you know, a 2-year-old mongoose that would be good at that, but don't use it for outside of that. And then we have these guys. Lurking variables and confounding variables. What that is talking about is a phrase that gets used a lot in correlation. And that phrase is correlation is not guaranteed to mean causation. In other words, X doesn't necessarily cause Y. Now, I think in this case, it would be reasonable to assume that the age of an animal is the main reason it is the height it is, right? As you grow older, you get taller, right? But can you remember the ones we did with things like the number of TVs that a country had in a household and how long they lived for? And each dot represented a country. And the data was quite linear. And you got a pretty good fit. But that doesn't mean that owning TVs make you live longer. You remember that that was an example where we had some other variable that was actually representing it. And if you remember this story, this version of the story, didn't we decide that the main reason was probably wealth of a country? Wealthier countries probably have more TVs per household. And what you're really measuring here is the wealth of a country has a direct effect on how long the people in that country live for, right? Wealthier countries, enough food, maybe too much food, but definitely good resources, right? Lots of medical care, medication, doctors, all the good stuff that keeps you alive. And so correlation is not causation. So you shouldn't ever really, unless you are absolutely certain that you've tried every other avenue of approach, that when you get a good linear relationship, that X is really causing Y. Not guaranteed to be true in every situation. Hopefully you found the main reason, but couldn't you have a lurking variable out there? Right. Something else that's the main reason. I think the other one I like to do, did I do the shoe size and reading age of children one, which is another version of this? Right. Where if you look at children's shoe size and what age they read at, it's a very good linear relationship. But it's not the fact that a child's feet are bigger that make them read better, isn't it? It's just the child's age. And you know, older children have bigger feet, and that's what you were really measuring. So try not to jump right in when you've got really good data and say, this is the cause of that. Because it might not be. And that's surprisingly common. Any questions? Maybe what I've done has made you think a little bit. Oh dear, poor Cannon. For the last few minutes, I was about to look at some sampling methods, and I will just talk a little bit about that as well. But try not to take too much from my opinions. I am a very opinionated person, as you probably know by week 10. I think you probably knew that by week 1. Just because I have a strong opinion or a weak opinion on something, it doesn't mean I'm right. In fact, if you ask my wife, it probably means I'm wrong. 9 times out of 10, I am. But I think it's always good to have a skeptical opinion of everyone, including me. But extra careful politicians. I'm going to have to get that one in. So figure out yourself, using your common sense, what makes sense. And don't always listen to my very biased opinion on all sorts of things. Okay, right, we got sampling methods. There are lots of sampling methods, but the holy grail is called a simple random sample. In fact, in many of the questions that happened from about here onwards, we're assuming that the data was collected as a simple random sample. Now, if I was doing a multiple choice, wouldn't I give you like 4 or 5 descriptions of what that meant? Can anybody try and put into their own words what a simple random sample of, say, 100 would be? How would you know you've got one? Silence is deafening. It's a simple random sample. Okay. Here's a kind of formal definition where any person in the population has an equal chance of being chosen. As any other person. So anybody in the population can get picked, and anybody in that population has just the same chance of being picked as anybody else. That's essentially the gist of a simple random sample. What makes that so powerful is that when you do simple random samples, don't you tend to get a fair representation of the population? Right, whatever that population happens to be, if you pick 100 people and it's a simple random sample, that 100 people typically is very similar to the big population. Now, we can't always get simple random samples. There are lots of other kinds of sampling techniques that you could use. Suppose I wanted to get 100 Olympic College students, and I decided I couldn't really do a simple random sample for whatever reason, but I wanted to still get 100 people. What would a systematic sample look like? Could you think of an example of how I could do that systematically?
Some organized way of picking 100.
Yeah, any
Wow.
organized way at all will do. And really your brain can go over them. Just off the top of my head, couldn't I just have everybody who's a student Olympic College and pick 5 people whose first name starts with an A, and 5 people whose first name starts with a B, and then 5 who starts with a C or whatever, and get my, whatever that would have to be, 135 students that way. Couldn't I just randomly pick 100 classes, and in each of those classes, just turn up and pick the first person who walked in the door? There's no limit to how systematic you could be, right? As long as it's something that's got a pattern. Couldn't I just take everybody in Olympic College, give them a number from 1 to the last one, and then just randomly like stick my hand in a bag and pull out some numbers? I guess that's slightly random as well, but I had a system to it as well. Maybe pick position 1, position 100, position 200, something like that. That would work. Oh, last one. That one might jog your memory. Right, cluster sample. Suppose I am interested in the opinion of nurses who work in hospitals, and I want their opinion on euthanasia. That's a pretty depressing thought, but euthanasia is, right? And I decided to use a cluster sample. How would that work?
Would that be like you pick floor 8 and you take those nurses that work on floor 8? Or would that be like systematic?
That's closer to being systematic, but quite a lot of these kind of blend in each other. I mean, the opinion in nurses at hospitals in America, so we'll make it really big population. So any nurse who works in an American hospital, right? So they have to work in a hospital and it has to be in America. And I want to know their opinion on euthanasia. And I want to use a technique called cluster sample. I could do it in what way? Can I randomly pick 5 hospitals in America? And then just go to each of those hospitals cluster and ask every nurse in it. That would be one way to do it.